Welcome back, students, to our second lecture here for thermodynamics. So last time we learned some of the basics of thermodynamics. We went through some of the definitions. We talked about the system as a region of interest, and the surroundings was therefore everything else besides our region of interest. And what we're going to do in this class is start by considering systems that contain ideal gases. And from there, we're going to look at more complicated systems once we've set the framework of thermodynamics using ideal gases that we're somewhat familiar with. And eventually, we'll extend our thermodynamics ideas to real gases, liquids, and we'll do chemical reactions as well, and see what we can learn about all of these processes and states of matter using thermodynamics. So for today, what we're going to be focusing on is heat, work, and the first law of thermodynamics. Now, some of these things, I'm sure you've heard of all these words before, but you probably haven't quite heard of them in the context that we're going to use them in this class. So let's go over the learning goals. The learning goals for this lecture are going to be to apply the first law of thermodynamics. So we'll see what that is. It's pretty straightforward and how we apply it. Then we're going to learn about heat and work, and at the end, you're going to want to be able to state the properties of heat and work. So get an understanding of what heat and work are and what we mean when we say them. And the last thing we're going to do, the calculation part for today, is we're going to apply heat capacity. And with the heat capacity, we are going to begin to be able to address how the internal energy changes as we change the system. Okay, so we're going to be talking about the energy of systems. So what do we mean when we talk about the energy of a system? There's a lot of kinds of energy of systems, and you're already familiar with two of those kinds of energies, say enthalpy and free energy. We're not going to talk about either of those today. We'll actually mention enthalpy a little bit at the end. But we're going to start by talking about the internal energy of a system. And we might ask the question, well, what is the internal energy of a system? And we have an example of a system here. This is something like we've seen before last semester. So what we have here is simply a group of particles in a box. And these particles have energy. So these red lines here are simply the energy levels of a particle in a one-dimensional box. And you probably don't remember that equation, but you can grab your textbook, you can open it up to the particle in the box chapter, you can find the equation, and you could figure out the energy that this system would have just based on with its distribution of particles. So this system has a certain amount of energy. So one of the questions we're going to ask is, how can we actually physically change this system in order to get the energy to change? And so looking at this setup, you could say, well, the energy would change if we had a different amount of particles on each energy level. So how can we do that? Well, one pretty easy way to get particles on different energy levels is to increase the temperature. So here, this is this is the same figure as is over here. And this is an example of the energy distribution that we would expect at 0.2 Kelvin. And way later in the semester, we'll kind of figure out why it has to be so cold to see something like this. But just take my word for it here, or do the math if you want. And we'll do that on the homework. So I guess you better do the math. Now, if we increase the temperature to 0.3 Kelvin, we could say, well, adding more temperature is going to allow these higher energy levels to be accessed. And you can see that here as well. So this energy level here now has two molecules occupying it. And this one that had none now has one. And we can see a general increase of these as a function of temperature. So we can calculate the internal energy. And this is what you're going to be doing on the homework. And this is simply, again, using the particle in the box model. To get into units of joules per mole, you multiply the actual energy you get, which is going to be very small amounts of joules, by Avogadro's number, and that tells you what a mole of particles would be doing rather than just one. And so we can see that, of course, by adding temperature into the system, we are more likely to be at higher energy levels. So this tells us that our internal energy is a function of temperature. Now, interestingly enough, our internal energy is also a function of volume. So What do I mean by that? Well, again, consider this. We can go and calculate this energy. It's the same as it was before. It's the same system. But what happens if we compress the system? Well, you'll remember that the energy of a particle in a box is related to the box length. So if we make the box smaller, we actually see more quantization. So you can see here we're shifting. The energy levels get higher, but they also get spaced further and further apart. So we can see with these red arrows here that we're going from having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 levels access to only having 1, 2, 3, 4, 5, 6, 7, 8, 9 levels access, but this 9th level is way higher than the 10th level. So that in fact actually increases the energy as a function of volume here. Now this is true for real gases, but not ideal gases. So we're not going to focus on this yet, but we will see this in the next couple of lectures. So we can use quantum mechanics to figure out what the internal energy change of a system is when it increases in temperature, decreases in volume, or any other combination of these things. But we don't have to do this. We can use bulk properties of the system, and that's basically what we're going to be doing for the next month or so. So how do we do this? Well, we do this using the first law of thermodynamics. So we already saw this on the last slide. We use the internal energy that we give the symbol U for. The internal energy simply talks about how much energy is in the system. So the internal energy is simply the sum of all of the energy levels that a molecule has, and then the sum of all of the molecules that are in the system, and then you get the internal energy. And that's what the internal energy is for now. We'll see later that you can also store energy in other ways. For example, chemical bonds store energy, and when those bonds break, they release energy, and that changes the energy of the system and so forth. So we'll talk about chemical reactions eventually as well. So what is the first law of thermodynamics? The first law of thermodynamics is also known as the law of conservation of energy, and you'll be very familiar with that law from Gen Chem. So the first law of thermodynamics says that the internal energy, which is U, of an isolated system is constant. Now that doesn't quite sound like the energy of the universe never changes, but the universe is an example of an isolated system like we talked about last time. So if the universe is an isolated system, then the internal energy of the universe can't change. It must remain constant. So what do we do with this law? Well, this law tells us, for one, that energy can't come from outside of the universe. We have a set amount of energy in the universe, and that can't change. What we can do with this is use this law to figure out what happens to a system. So can the energy of a system change? Well, of course it can. We just saw 2 examples of how the energy of a system can change. So what's happening then? If I add temperature into my system such that the internal energy increases by about 0.3 joules per mole, where did that energy come from? Well, it had to have come from outside of the system. So what we can do is if we consider our system, and then we also consider the surroundings. Remember with our definitions, our system was the part of the thing that we're interested in, and the surroundings is everything else. So if we're considering the thing that we're interested in along with everything else, we are in fact considering the entire universe. And that means we're considering an isolated system. So we can say that the delta U total for our system plus surroundings is equal to 0. It forms an isolated system. We can also, from this, say that the internal energy change of the system is always equal to the negative change in internal energy for the surroundings. So for example, if my system increases by 10 kilojoules per mole, that energy didn't appear in the system from nowhere. That can't happen. Energy must be conserved. It had to come from somewhere else. It had to come from the surroundings. What you'll note here is that we stopped talking about U and started talking about delta U. Now, the reason we're doing that is because if we're saying the internal energy of an isolated system is constant, we don't know what that is, but we do know that if we tried to change it, we couldn't do that. So the internal energy of the universe might be 100 billion trillion, megajoules or something. That's probably way too small, but it must be some number. And it doesn't really matter what that number is. We can just say, well, it can't change. It has to be constant. We don't need to know what it is. We just need to know that it can't change. So when we consider a delta U, we can set that equal to 0. We also like our zeros a lot whenever we're doing math. So that's why we're talking about the language of delta U. You'll be familiar with this as well from talking about things like enthalpy and Gibbs free energy. And this also reflects the fact that we don't really know what the energy of a system is. And we also don't really care what the energy of a system is. We just want to know how the energy of the system changes as we go from state 1 to state 2. So we'll typically talk about deltas here. Now, the next question that we have is, okay, so we know that the internal energy of an isolated system is constant, but if we have an actual system that's not isolated, they can exchange energy with the surroundings and it can change. So how can it change? From our first law, we can also get that there are only 2 ways that we can actually change the internal energy of a system. And what we'll say then is that the change in internal energy, delta U, for our system is equal to the 2 ways in which it can be changed. So it's equal to the sum of the heat, which we give a little q, and the work, which we give a little w. So if we know how much work went into or out of the system, and we know how much heat went into or out of the system, those are the only 2 ways in which we can change the internal energy. So if we know those 2 things, we can put them together and figure out how the internal energy of the system changed. We'll start by considering work, and then we'll look at heat and see how these things actually change the internal energy. Work is described as any quantity of energy that flows between the systems and the surroundings that can be used to change the height of a mass in the surroundings. So again, this kind of sounds pretty weird in terms of what our definition for work. Let's go to the whiteboard real quick and we can do some writing. From physics, you may remember that work is equal to force times a distance times a delta x. And in some cases, we will talk about work in this way. What we're going to do more often in this class is use integral calculus to describe things. So rather than having work be equal to f delta x, we'll say that work is equal to the integral of f dx. Now, if f is not a function of x, they end up being the exact same thing. Now, we're talking about, like I said, for the most part, ideal gases. And ideal gases don't move masses, distances often. Sometimes they do. So if you have a gas in a piston, that piston expands and that piston has a weight, it's actually lifting a mass a certain height. And we'll do those calculations sometimes. But more often what we're going to do is instead consider the following. So we can take our force and we can convert this force into a pressure. So what the force is, right, a pressure is equal to a force over unit area here. So we can say that our force is equal to a pressure times an area. So we can go here and say, well, we have a force, which is equal to pressure times an area dx, take an integral of that. And in a lot of cases for gases, say you have a balloon, you don't just expand the gas in one direction. So a piston certainly would expand in one direction, but a balloon would expand in multiple dimensions. And then what we actually have is not a simple single integral here, but we have a double integral where our pressure, we have a pressure that's changing as a function of area and position, or x. And we can also just boil that down to the integral of p dv as the volume changes. Now, we'll see in the next couple of slides that typically we'll write a negative sign here. And that has to do with the sign conventions that we say for work. And we'll see this more on the next slide. But what we have for work in terms of ideal gases is that work is equal to the negative integral of the external pressure, and we'll talk more about what this is again in the next couple of lectures, times the change in volume dv. Now, depending on the system at hand, this integral will have very different solutions, and we'll see some of that in the next lecture. So now that we have the definition of work as being the negative integral of p dv, what is actually happening? How do we actually do work on a system? Let's consider a system that is a piston. So we'll have a piston here that has a mass on top of it, and this piston is set at a certain height by the stopper here. And this system has an initial pressure and volume, and also temperature if we allow the temperature to change. What would happen if we were to remove this stopper? Well, you can imagine that probably this mass is going to push down on the piston and compress the system. So when this happens, we end up with a new pressure and a new volume. And what we say in this case is that work is done on the system. So work is added to the system, and we give a positive value for work here. This kind of explains why we had that negative P delta V. In this case, delta V, the final minus the initial state, is negative. So if we want the work to be positive, we need a negative sign there. Pressure is always a positive number, so the only positives and negatives come from delta V. We can also have the system do work. So we can imagine a case where we don't do a compression, but we do an expansion, where we have a system that's at a pressure and a volume, and that actually raises and lifts a mass. So in this first case, the mass is lowered, work is done on the system. In the second case, going backwards, the mass is raised, and that work is done by the system. I want to note here something that's actually pretty important and can be really easily missed. Naively, we would expect if, so say I had a gas at atmospheric pressure, then I dropped a mass on it, say that mass exerted a pressure of 1 bar, we would expect the system to end in a final state with atmospheric pressure plus the additional pressure of 1 bar. So we'd expect the system to be at 2 bar. And that's true if we allow that to happen, but we don't have to allow that to happen. So in this case, the mass is added and the gas is compressed, but there's another stopper here. So this final pressure does not have to be the external pressure that was applied during the compression. It often is, but it does not have to be. And this is really one of the challenging parts of this class, is actually basically it's reading comprehension. So can you read a problem and comprehend what that problem is asking you to do? And it is probably one of the more difficult things that we will do in class. And hopefully we'll have a lot of opportunities in class to actually go through some examples of this, so it's not so intimidating. One very important thing to note about work is that work is transitory. So what do I mean when I say that work is transitory? Basically, I mean that work does not exist on its own. So for example, if I have a balloon and I ask you what is the work of this balloon, that is not really a question that we can ask. So that balloon has a pressure, it has a temperature, it has a volume, it has an internal energy, it has an entropy associated with it, but it doesn't have a work. Now, if I took a balloon and pumped air into it, and now I had an initial state and a final state, work is done as I went from one state to another. So work is a way that a system can gain or lose internal energy. I mentioned this on the last slide, but work has these sign conventions that go along with it. If we have a negative work, it means that energy is coming out of the system. So the system is doing work or could be getting colder to do this. And think about this very much along the same lines as delta H from Gen Chem. So if we had an endothermic reaction, energy needed to go into the system. Here we have, again, similar sign conventions. So having a negative work means that energy is leaving the system. Having a positive work means that energy is going into the system. Energy is being added to the system. The system could be getting warmer, or the work is being done on the system. Another thing to note, I mentioned this last time, but when we have pressure times volume, like we just saw on the last slide, that is a form of energy. So we can convert the units of liters and bar. If we have 1 liter bar, which we get by multiplying, say, 1 liter by 1 bar, this is equal to 100 joules or 0.1 kilojoules. This is something to keep in mind in a conversion that we'll be doing often over the course of this class. I'll just briefly show this here that there are other kinds of work that are possible. For this first part of class, we're going to be focusing exclusively on expansion work, so negative PdV here. However, we will go over in the next month or so different kinds of work like stretching, bubble expansion, and then electrical work. So we'll see these as well, but we're not going to talk about them too much yet. The other way that the internal energy of a system can change is with heat. So heat is very similar to work. So work was any energy that came into or out of a system that could raise or lower a mass. Heat is any energy that goes into or out of a system that causes a change in temperature. So in this picture here, we see an example of a calorimeter. We'll go through the calorimeters in much more excruciating detail in about a week and a half. But heat is, again, very similar to work. It has all of the same properties that work does. So heat is also transitory. It has the same sign conventions. Certain systems don't have heat. Heat only makes sense going from one state to another state. And this is because heat and work are examples of path functions. So the focus of our lecture for next time will be about path functions. So we're not going to go into that too much right now, but path functions are functions that can be different depending on the way that the system traveled from state 1 to state 2. So these are strange kind of functions, and we'll see how we work with them next time and in the coming weeks. Now, how can we talk about a system gaining or losing heat, and what does that mean for the internal energy? The connection between heat and internal energy is in fact the heat capacity. So hopefully you guys remember heat capacity from a previous chemistry class. Heat capacity is simply a property that reflects how a substance temperature changes in response to heat. So going back to the whiteboard here, we can talk about what heat is. So like work, which was equal to the negative integral of P external dV, heat is equal to the integral of the heat capacity C times the temperature change, dt. So you may remember a heat capacity from high school. I think I do. It was burned into my memory, this number 4.184. And this 4.184 was the specific heat for water. So more specifically, this was 4.184 joules per gram per Kelvin. And what this number means is that it takes 4.184 joules of energy to increase the temperature of 1 gram of water by 1 degree Kelvin or degrees Celsius. Now, we talked about these last time, but our heat capacity is an extensive property. It depends on the size of the system. If I have 1 gram of water, it's going to take 4.184 joules of energy to increase that by 1 degree. If I have 10 grams, it's going to take 41.84. If I have 100 grams, 418, and so forth. So what we'll do is more often write this in terms of a heat capacity in joules per mole Kelvin. So our heat capacities will be written in these units, and this will make our extensive property an intensive property. So water only has one heat capacity in terms of joules per gram per Kelvin or joules per mole per Kelvin. And that doesn't change whether I'm talking about a gallon of water or a cup of water or an Olympic-sized swimming pool worth of water. So how can my heat capacity change? It depends. So we'll look at some figures of this. I want to do the math while we're here. And we actually have two different ways we can talk about adding heat to the system. So one way is if we have a container that is rigid. If I have a rigid container, it is not possible for this to expand. So the gas in this container will not expand. So if I have a V1 and a T1 here, we have a certain state. Now, if I add heat to this system, so let me add some heat here, what will happen to it? Well, the volume will not change. despite me drawing a skinnier cylinder here. So the volume of this system will remain unchanged, and what will change is the temperature. So my delta V in this case is V1 minus V1 equals 0. So that means my work, which is equal to the negative integral of P external dV, is also equal to 0 here. So there's no work possible. So my change in internal energy then is simply, well, it was heat plus work, but I know my work is 0. So it's simply my heat. And in this case, note that we have heat at constant volume. So I'll give this heat this subscript V here. Now, what is my heat at constant volume? Well, it's simply equal to the heat capacity dT. And so we'll say that my heat at constant volume is equal to the integral of the constant volume heat capacity times dT. In most cases, the heat capacity of substances is not really temperature dependent, which means that CV is approximately a constant for most temperature ranges. And then I can change this integral to be CV times the integral of dt, which is then CV delta T. And what I'll often do, like I said before, is we'll convert this into a molar basis. So my delta U is equal to N, the number of moles, times CVM. So CVM is this heat capacity in joules per mole Kelvin. And then we have our delta T here. So what this says is I want to know how much my energy has changed. And I have my number of moles. I'm multiplying this by a heat capacity that's in joules per mole per Kelvin, and then a temperature change in Kelvin, which gives me joules. So this heat capacity is converting a measurable temperature change into a heat. And if there's no work, that heat is directly related to my internal energy. Now, what if there is work? So what if I don't have a system that is rigid? So for example, if I have a system that looks like this, where I have a gas and I have a piston, this piston can move. I have a volume and a temperature. I add heat to this system, and now what happens? Well, now what I end up seeing is I see expansion. So I reach a new volume and a new temperature. So what has happened? Well, in this case, we have had a change in volume. And my internal energy is still heat plus work, but now my work is not 0, it's an actual number. It's whatever the pressure is times the change in volume. So if I have a constant pressure, I can come up with a special scenario where I have a constant pressure heat capacity that's equal to delta U minus W. And delta W here is simply equal to negative P dV. So this gives me delta U plus P delta V. What I'm going to do here, and we'll talk about this more in the next couple of lectures, is define a new special function because I really like this relationship. I like this relationship up here where I have delta U is equal to QV. Now, delta U is not equal to QP, but maybe something else can be. And so what we'll do is define a new function, delta H. And we'll go through this in more detail next time. But we got this by defining a function enthalpy that's equal to U plus PV. In doing so, we can now say that our heat at constant pressure is equal to a delta H. And the reason for this will become obvious as we continue working with these. This is why we know delta H and not delta U. So for every chemical reaction we've done in the lab, we've done it on a benchtop where the pressure was the constant atmospheric pressure. And so the heat that we measured in those sorts of processes is directly related to the enthalpy, not the internal energy, which is easier to apply for constant volume processes. In the case that the pressure and the volume are all constant, then delta H is equal to delta U. And that's often kind of the scenario that we're in. What we can also note here is that QP, our constant pressure heat capacity, is always going to be larger than QV, our constant volume heat capacity. Now, how can we say this? Well, look at the diagrams we've drawn. In the constant volume case up here, the volume remains constant. So every joule of heat that's added into the system goes into changing the temperature because it doesn't do work. Here in the bottom where the pressure is constant, work is being done. So part of the energy that's added in the form of heat goes into doing work. So it takes more heat to actually increase the temperature by 1 degree because we also have to do an expansion in order to keep the pressure constant. So we have this relationship that the constant volume heat capacity is always less than the constant pressure heat capacity. And we'll see this more towards the end of class. But what we can actually have a mathematical expression for this and say that the constant pressure heat capacity here in molar units is equal to the constant volume heat capacity plus the gas constant R. It also turns out, for reasons that we'll talk about later, the constant volume heat capacity for ideal monatomic gases is 3/2 R. For other gases, it's different, and this is based on the degrees of freedom, and we'll talk about this later in the semester. So here we can see some figures from the book that were going over the same sorts of things that I was drawing on the board. And we can also see, I want to talk about this for a little bit. I believe this is for chlorine. It's for some strange gas here. But we can see what happens to the heat capacity as a function of temperature. So some phases of matter, namely liquids and gases, have pretty constant heat capacities based on their state of matter. So for example, we can see that for this substance, the heat capacity at 300 Kelvin is about 30 joules per mole per Kelvin. It's also about 30 at 400 as well. You can see it does increase slightly, but it's pretty constant. So if we were to figure out the heat by assuming the heat capacity was constant and taking 30 times from 300 to 400, we would have 30 times delta T of 100. We would be pretty close to the actual heat of that process. Now, we might properly want to integrate it as a function that's estimated based on a polynomial. We can do that. We would have to do that for the solid. So if we wanted to know how much heat it would take to get the solid from 0 Kelvin to 100 Kelvin, and we assume the heat capacity was constant, we would get a totally garbage answer because it's a very bad assumption. However, for something we can see for liquids and gases, it's pretty good. And it would also be pretty good for solids too if our change in temperature was like 2 degrees. If it's 100 degrees, it's not very good, but if it's a small change, assuming it's constant, is pretty good as well. So something to note here, and this is another challenge that we'll have in thermodynamics, is that we have many values and many expressions for things like heat and work. So we'll see a lot of this in 2 lectures from now. One of the challenges we'll have with thermodynamics is sorting out which equation to use for which situation. And kind of going along with that, there's another challenge that we have to accept that these relationships are always true. So on the board, I wrote that delta U was equal to NCVM delta T. That relationship is true. It's always true. It doesn't matter if the process we're considering actually happens at constant volume. The change in internal energy is still equal to the number of moles times the constant volume heat capacity times the change in temperature. And so this can be a kind of hard thing to wrap your mind around, that it doesn't matter if my system actually is at constant volume, because the internal energy is equal to the constant volume heat capacity times n delta T. And so I think practice will be very helpful in getting these sorts of things down. And that's what we'll do a lot of in class and on the homeworks and quizzes is going through and practice these ideas. The last thing I want to mention before I let you guys go is just another quick set of definitions. So there are a couple of words, and we'll use isothermal very often in class. So an isothermal process is a process that occurs with constant temperature. And we'll hear that all the time. There are complementary words that go along with that. So we have isobaric and isochoric. And so these are for changes with constant pressure or constant volume. We will very often consider constant pressure and constant volume changes, but I think more often those are referred to as constant pressure or constant volume changes. You might come across, if you're looking through problems in the book, you might come across isobaric and isochoric, and that's what those mean. So if we have a system where the pressure, temperature, and volume are all changing, that's much harder to deal with than a system which only one of those or two of those things are changing. So if you hold one of those things constant, then the pressure change is directly related to the volume change and so forth. And so we'll do that when we can, but in some cases we can't. So we'll leave this for now. And next time we're going to look more into heat and work, specifically as to how we can describe the heat and work for processes.